We can sometimes extract what we call bonus results from the Fourier series representation of a function. For example, the periodic function described by f of t equals t between 0 and 2 pi with period 2 pi has this Fourier series expansion down here. The points listed in brackets that are accepted are those where the function has a discontinuity, and therefore the function value and the value of the Fourier series at these points are not the same. If we substitute t equals pi on 2 on both sides, we will get f of pi on 2, which, given that f is equal to t between 0 and 2 pi, is simply pi on 2. That is equal to pi on 2 substituted into the Fourier series for t. So it has to be equal to pi minus 2 times sine pi on 2 plus a half sine pi plus a third sine 3 pi on 2 plus and so on. Now if I rearrange this, I will get pi over 4 is equal to what's in these brackets here, sine pi on 2 plus a half sine pi plus a third sine 3 pi on 2, and so on. Now, as it turns out, sine pi on 2 is equal to 1, sine pi is 0, sine 3 pi on 2 is negative 1, and this pattern continues with the next one being 0, then 1 again, then 0, then negative 1. So what we can do is write this as 1, and then what's left here is 0, and there's a third here, so we've got minus a third, and it's plus 1/5 minus 1/7 plus, and so on. And of course we now have a representation for pi on 4, which can be written like that. That means we could also rearrange this and write this as pi equals something, and in this case that is pi equals 4 times 1 minus a third plus 1/5 minus 1/7 plus, and so on. So we now have a way of estimating pi. That is our bonus result. And if we wanted to write this using a series, we could write it like this. It is 4 times the series from n equal to 0 up to infinity. And of course we've got a minus alternating, so we've got minus 1 to the power of n. And we only have the odd numbers in the denominator. So I'm going to write this as 2n plus 1. Here's our bonus result.